Okay, so welcome to our second class. As I will do for the rest of the semester, each class at the beginning, I will spend maybe 10 minutes to 15 minutes to review what we discussed. And let me first share my screen. If you want to find out all the information, instead of I putting on the canvas, it was on my website. So you can go to teaching material this semester, right? So you see that I put more information, especially for each lecture, like lecture 1, I have a video. So if you want to review, so feel free to do so. And these are the slides. And first of all, the homework. Let me double check if any student waiting. Probably not. Yeah, there are 13 students. Okay. And also I gave a homework assignment, which is due in 2 weeks. If you want to know the due date, everything is in the course outline, right? So if you recall this, so today is the 27th, the due date will be February 10th. And I will open up a slot for you to submit your homework through Canvas later this week. Okay, so let's take a quick look of homework. Most of the homework problem, I will get it from the textbook. So in this case, we have a chapter 1, chapter 4. Chapter 4 is about greedy algorithm we discussed today. And in addition, I give you sometime my own questions. So for example, question number 3. And this we assume that you already know the material, it's just a review. Like how you rank this order, right? So order means that start from the low to high. And you can put in terms of complexity, it's the same thing. We call this equivalent classes. Right? And can you rank them and put them in the different classes? So that's the assignment. And the question number 2 is about stable marriage problem. Right? And we ask you to show that if we change 2 gender into 1, show that for any given even number, for example, 4, 6, 8, 10, 12, and so on, there always exists a preference order. So order means that the amount is 2n persons, such that stable pairing among 2n do not exist. So that means you can always find an unstable situation. So you can start with the 2 and 3, and then you generalize the conclusion for any n. So your solution is for any n, right? Without give a specific order, maybe some kind of a general structure. So this is the one. And all the other ones just from the book. And if you have any question, you can either ask during the class or you email me after class on homework. Any question about homework assignment?
Yes, this chapter 1, 4, does that mean like the 4th exercise from chapter 1 or
Yeah,
something?
yeah.
Okay, thank you.
So like a chapter 4, question number 2. So, by the way, the good things about this book is that there are so many exercises. Many exercises are from real world. So they also put it in a very nice way, give you a story and then ask you to solve it. So it's very interesting. It's not really boring. Okay, so let's review what we discussed last time. We start with,
Professor, I have
yeah.
one question. So all editions of the book will have the same exercise as number 4, is it?
What's your question?
So like you want us to do the 4th exercise from the book, but books will have many editions, right?
Oh, there's only one edition.
Oh, there's only one. Okay.
Yes, there's only one edition.
Okay. Thank you.
Okay. So let's quickly review the material. We discussed lots of things, right? So I think we need to do is focus on a couple of important things. And I also give you some fun problems. So this is what I plan to do every class. Maybe give you some kind of bonus problem to see if someone can solve it. Like last time we mentioned about celebrity problem, right? In Oscar, then the run-up team in Super Bowl. And then more interesting things about, we discuss a different type of algorithm. In fact, throughout your study, Temple, maybe other places, most of the data structure, programming technique, or algorithm focus only on one type of spatial algorithm called sequential algorithm. So meaning that when you solve problem, you follow step, right? 1, 2, 3. Sometimes you have a jump and a loop, but that's still sequential. There are many types of algorithm. We discussed a couple of examples called randomized algorithm or probabilistic algorithm. If you recall last time, right? Like doing a survey on the popularity of a former president, we can do some kind of probabilistic algorithm for the purpose of keeping privacy. And sometimes you have a randomized algorithm, which is more efficient than deterministic algorithm. All the algorithm you learn is deterministic algorithm, except like a quick sort. You randomly pick a number, right? They partition the array based on this number, larger or small. But there's one set of problem which is interesting called parallel algorithm. So I give you this example called bitonic sort. So how you read this one, each line, horizontal line, is one processor, which is like a one person. So doing basic things, you pick another processor, do comparison, large or small. So in this case, it's like a 16 processor. So there's a concept called linear speed up. So for example, if a job, one person, you spend 100 seconds to complete. Now the question, if you deploy 10 processor, can you complete in 10 seconds? So this means a linear speed up without slow down. The interesting thing is that most of the cases it cannot, because there is some synchronization and overlap. So you don't get that kind of linear speed up. You can increase the increase the execution time, runtime is faster, but you don't get the linear speed up. So this is a very good example. If you deploy the n processors for n number, the best you can do is log n squared. So if you time n times log n squared, so you can see this number is larger than n log n. We know that sorting algorithm, the best sorting algorithm is n log n. So you can see that there is some kind of overhead of log n. It's not too big, but there's some overhead. So the parallel processing is really fascinating of parallel algorithm. It means that how can you design the most efficient algorithm? Give you a certain number of processor. What's the best speed you can get? Or you can ask a question in many ways. For example, what's the maximum number of parallel processor you can use so that your speed up is still linear? Okay. So by the way, if you times number of processor with the execution time, sometimes we call it efficiency, compare with the optimal sequential algorithm, In this case, efficiency is not 1. Obviously, you want to keep a good efficiency. So there's a nice trade-off between efficiency and the speed up, right? So this is obviously not the focus of this class. You can spend the whole semester to talk about parallel algorithm. But more interesting things about distributed algorithm. Distributed algorithm means there is no central coordinator. So the most famous distributed algorithm, in addition to this blockchain, is that the algorithm we discussed last time about stable matching, right? Stable matching. So let's quickly do this stable marriage problem. So stable marriage problem is that you have n men or n women or n boys and girls. You want to pairwise match them. And you need to satisfy certain condition. Means that eventually everyone will get married and they should be stable. Stable means that you will not have a situation that divorce other things. Although they may not get the best they want, but the divorce situation will never happen. So it's a very interesting problem. Why this algorithm is so fascinating? Probably we did not emphasize too much. If you look carefully, this is totally different algorithm than all the algorithms you learn in other classes. First of all, it's a distributed algorithm. Means a couple of things. Means that there's no central controller. No government force you say that when you should marry, when you should start dating. Everything is asynchronous, right? Asynchronous. And no one control your time, everything, right? And eventually it was stable, means that you complete the matching process. Right? So the algorithm work in a very nice way. It distributed. Another one is like a privacy. What do you mean privacy? Means that people do not want to reveal their preferences, okay? So no one knows other person's preferences. So that means everyone now talking about big data, right? So this is a big issue, means that how, if we collect all the data, how you ensure the privacies. So this is a private algorithm, means that everyone keep their preference. Right? So it works as follows, very simple. It's like a normal life. You start with a boy, propose the favorite girl. So when girl received this proposal, she either reject or engaged. Right? So engaged means that currently she has no other date, they engage. So when she reject, if not already available, means that you're married. Or you already engaged, the person you engaged to is better than the current boy, the other boy who proposed you, right? So the girl is always in the engagement once someone proposed. And what happened to the boy who got rejected? Then he will go for the second one. Just repeat the process, right? So in the order from the best, second best, and all the way to the last. Then this algorithm has a nice property that eventually everyone married and there is no instability, means all stable. Right? No one want to do swap. Okay, so this is about what we learned the last time. So that's the main things. Obviously, we focus not just on the design, we also focus on the complexity, right? Means analysis. We found out that the complexity of this algorithm, although it's asynchronous, you only need to do n squared operation. Operation means that how many times boy will propose, right? So the maximum time each boy is n. The n times n squared. So that means this algorithm will terminate, okay, although it's asynchronous. So that's why we showed how we analyze this. And also there are many other properties, including eventually everyone got married and marriage is stable. So you will learn throughout the class how to learn how to prove something, how to prove the complexity of algorithm, or find out the complexity and prove, and how to prove the correctness or property of various algorithms. Okay, so that's the quick summary of last class. Any questions? Anyone want to ask questions? If not, let's look at some extension. Let's see if I can find my extension. Okay. So this is a good example. Or maybe this is the one I ask you to solve it if you have a time. So this is just another way to look at the algorithm. Somehow there's a bar, it's kind of annoying. Don't know how to move this. All right, so this is another way to look at it's a very nice visual way. So you can see the left-hand side is a boy, right? List of a boy. Right-hand side is a list of girl. And each boy has a preference. So first boy is a C, B, E, A, D, means he prefers C, the best. B, second, E, and so on. Last one is a D. Girl has also the preference. So boy is labeled 1, 2, 3, 4, 5. Girls are labeled A, B, C, D, E. Okay. And suppose this is a current marriage. Current marriage. You can check whether it's stable or not stable, right? That's we already learned. At least everyone's married, right? But they don't get the best that they want. For example, for the girl A, she prefers 3, but she's married to 2, right? Actually, 2 is rank number 3rd in her list, right? So the same thing for the boy. Boy 1 prefers C, and oh, he's happy he gets married to C. Although girl C prefer 4, okay? So that's kind of interesting, right? So, but it's still stable, although the girl is not very happy, but she cannot find another suitable man who's willing to break the marriage for her. So this means stable. And really interesting property is no matter what's the preference, that's the homework I asked you to do, right? Asked you to do question number 2. That can you come up with some kind of preference order among boys and girls, right? But in this case, it's one sex, which is a roommate problem. And everyone has a preference for the other one. Can you come up with some kind of preference so that stable pairing or stable marriage are impossible? Okay, so that's the situation. Now let's make the fun of it. Let's look a couple extension. We talked about last time presidential election. We look at a couple of interesting problems about election. Now it's after the election. So what typically a new president does is to change the policy, right? Change the policy. Imagine that the new president one day make a dramatic policy change. Means that we need to favor girls, not the boy. Remember the protocol we do is like favor boys, right? Although this marriage is stable, but boys started proposing, and eventually boys will get better on average than girls. Now, one day the president decided that from now on, we give all power to girls, not to the boys. Boy, no power. Let's the preference decide by the girls, right? So just go after the boys she preferred most. But that's a problem. The many advisors of the president say, President, you cannot do that. This will cause instability society for a couple of reasons. Because currently they all married, stable, right? So when you implement this policy, and not just divorce, but also there will be fight among all the girls. Because you may have a situation, 2 girls, multiple girls like the same boy. So who you should assign this boy to which girls, right? So let's make a story more fun. So suppose this president say that I respect science. So I'm going to ask some professor in UPenn. Okay, Wharton, start with economics, because it looks like this is economic problem. So say that if you can solve problem, I give you $3 million. So UPenn professor Wharton, they're very rich. They think that, oh, it depends on how many people involved. It turns out you have 80 million. So let's say 80 million people you need to swap or whatever. They said it's not enough money. So what I can propose, I give you some kind of policy, just one word, trade. All right, so that's a very favorite term called trade. So I would take the money, but I give you a really nice principle called trade. Then the president's office said, no, you just give me one word answers. Does not cost 3 million. So I give you $500,000. So before we talk about this trade, so let's understand what means trade. Let's just give a very simple example. Suppose US and China want to do trade. So what's the purpose of trade? Trade, the main purpose is try to get the better, right? Want to improve. For example, in China, maybe they produce lots of clothes, so have excessive amount of clothes. But US need a little bit more clothes. But in US, they produce lots of beans, right? Beans. So China like to eat beans. So why don't we do this? Just exchange, right? So you exchange bean with clothes. So after the exchange, we call trade. Both sides benefit. So that's a nice trade. It means a trade between two parties. But trade can involve multiple countries. So why is that? Let's just look at another scenario. Suppose the US want to do trade with Mexico. And US, especially in some states, for example, they need lots of labor. So to grow whatever beans or corns or this, you need a labor. So why don't we get some kind of cheap labor from maybe Mexico? Okay. But maybe Mexico government does not like it. Say that, okay, if we give you labor, whatever the price, but you need to give me something. So US government say, okay, I can give you lots of bean. Then government say that, Mexico said, no, I don't want the bean. I have enough bean. I want clothes. I like a Chinese clothes. So how do you do that? So what you can do is that the government US trade more bean with China, get more clothes. Then these clothes can trade with Mexico. And then the government, then they get labor, they can produce more red beans or beans. So you can see that as a result, all sides get benefit, right? So that's a trade. So that's the main idea of a trade. See that, the trade. Now the question is this one. So UPenn professor say that the trade is very nice, but president office is still not very happy. Not very happy means you can do trades. So how can you perform those trades, right? So that there will be no fight among the girls. So let's look at the one scenario how we do the trade. So trade is not based on like a two-party, two girls trade with husband. You can have a loop or cycle. So let's just look at this example. You see the bottom there? So what you can do is for the girl start with A. Her preference is number 3, boy, right? Although currently she's married to number 2, so she's not very happy, but she has all the power. So she wants to get the number 3, right? But number 3 guy has no power. He can only ask the wife. What's her current wife? Current wife is number D, okay? Number D, see this wife. So this wife is D here. Then D will check. I would prefer number 1 guy. So number 1 guy is there, right? Number 1 guy. The number 1 guy, yeah, see, yeah, wait. Yeah, number 1. But the D is not number 1. Yeah, number 1. But D is currently married to number 3 girl. Again, the 3 C will say that for this C, I prefer number 4, right? 4 guy. Then guy has no power, ask a wife. Current wife is number B. Then B, say, I prefer, best one is 5. So then you look at the boys 5, see the 5? And this one can continue. Oh, I think there's an error here. Yeah, I think I put an error. But in anyway, so you this kind of thing, situations like a boy to girl, girl and boy, then eventually you form a cycle. You form a cycle. So what means a cycle? Cycle means that it can shift, rotation, shift. So you can reassign based on this cycle. So this is a very nice property. This actually gives you a hint how to solve this problem. Right? Although I make a mistake here, and 5 actually not going to A, going to E. E we should continue, right? E was continue with 2, and 2 with A. Eventually go back to A. So there should be one more, 2 and A. This should be E. So once you form a cycle, they just a shift. So all the girls are very happy, right? So all the girls are very happy. Now, all this kind of shift and or trade, it's very involved in the sense that are you going to go for the number 1 guy or number 2 guy? What happened? Number 1 guy is no longer available, and then you go number 2 and number 3, and when should you stop? Right. So the president's office say, okay, I already spent $500,000. Then I will go to another Ivy League school, Princeton. Mathematics department say that how should I define a strategy or goal, ultimate goal, so that you know this trade will end. So they also give just one answer, say that Pareto optimal, Pareto, P-A-R-E-T-O. Pareto is the name of economics. Pareto means that everyone should get better off, right? So then if you can improve the happiness of a person, you just let the girl be happy, more happy, you know? until when she cannot improve. Or when she improves, she will hurt the happiness of the other girl. So that means Pareto optimal. So I mean, everyone try to improve unless this will hurt the other girl's feeling. So this is just very much like a trade, right? Trade means everyone's happy until you cannot do further trade. So this is done. Then president's office very happy, say, okay, but the problem is that looks like just one answer is too easy. I gave you $500,000. Then have another 2 million. Then you find out, oh, there's a real problem. Real problem is what? I know the strategy, I know the goal, but I don't know how to implement. So they probably want to go for MIT or another elite school. Then the advisor say, no, that's not politically right. We should be diversified. Maybe we can try Temple. Right? So Temple, they ask someone teach algorithm. So I will assign you this problem. Means that I already know the strategy is a trade, like this example, and you want to reach Pareto optimal. Pareto optimal means that all the girls should be maximum happiness, right? Without sacrificing the other one. And so how can you achieve this goal? And what's the best algorithm you can do? And after this algorithm terminate, you should get the Pareto optimal. Okay, and also algorithm should be very efficient. Okay, so this is the problems I give you. This is not too easy, but I think you can solve it. I don't expect you can solve it after the break, but so you can think about this. Any question? Or it's too complicated? No one tried to ask a question? The problem, I cannot see you, so no one opened the window. Any questions? I don't even see how many students are there. Okay, so this is one of the interesting problems you can think about. And in fact, you can make the problem a little more interesting. Just back to the previous stable marriage problem. And when we tempo accept this challenge, then we say, okay, why you charge $2 million? I say that I need to get all the preference from the girls, right? Then we do some kind of trade. Then the professor UPenn said, no, 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 this is not ethical because we to keep a privacy of all the girls. Now the question, can you design a distributed algorithm so that the preference order of these girls are keep a secret? You see this preference like A, 3, 5, 2, 1, 4. The girl will not reveal. Obviously, when she want to do it, she just proposed to the guy, number 3. Then the guy probably will say, okay, I cannot make a decision. I need to ask my current wife, which is number D. Then D will say, okay, I don't really, I'm fine, but I want the number 1. So you can see this a pass, right? It's a pass. Then eventually, once you find a cycle, then you're done. Now the questions are, once you find a cycle, so they're happy, then what should be the next step? Right? And also, do you always go for the number 1 preference? And when you should go to number 2 and should number 3? Right? And what's the complexity of the algorithm? Okay, so this is the first extension, so you can think about that. Then there are another interesting problem, and this is even more fascinating, is that imagine this policy being implemented for 1 year, then there are lots of protests in the country. Why is that? Because you gave all the power to the girls. What happened to the poor boys, right? Their preference never respected, especially their parents. Their parents are very upset because they spent 20 years raised this boy, got a good degree. Eventually, they cannot make any decision in terms of marriage. So what's the solution? Money. Right? So what you can do is that when the girls propose you, what you can say is that if you want to marry, we want to marry, I need a certain amount of money. Right? So actually, this is a very practical practice in many cultures. Right? Although usually boys make a proposal, girls just say that I need a certain amount of money for marriage. Now this money is interesting. Right? So although this looks complicated, but it's very easy. Just very simple because this is far beyond the scope of the class. I just give you some interesting things. So what you do is a buyer and seller. You can imagine the buyer is a girls, seller is a boy. Boy wants to get some money. So the money is this, or maybe this diagram. Right. So what you do is, so each buyer has some kind of valuation of all the boys. Means girl has like a score. You can imagine score is like how you're looking and something. Right? So like a buyer girl X has a valuation of a boy A 12, B 4, C 2, right? So this you can think this is the amount of money I want to get married. If I'm married A, I'm willing to pay up to $12. For the B is my second preference, I'm willing to pay $4 and so on, right? Now then everyone proposed to their preference, right? Then oh, I think this diagram has some problem. Okay, just this is the scenario. There are some issues here. Maybe I cut and paste is wrong. But just look at the C. Well, this may not be a good choice. Well, somehow the diagram B is not right. But just look at the C. C means that what X prefer, right? Preference. X prefer A because A is the highest value. And then each boy will propose the amount of dollars, say, I want to get whatever, $2 million in order to marry. Right? Whoever can match this $2 million. And we'll see how this the boy will increase its price based on the market. Right? So this is the situation. You can see that all the girls, X, Y, Z, all propose to boy B, A, right? So A means that A is very popular. Right? So immediately this boy A will raise the price. So how much you raise? Every time just $1 million. So after you raise to $2 million, situation slightly change. Why is it slightly change? And suppose the B also get the proposal and then ask for $1 million. You look at the Y, which is very interesting, Y. Look at the Y's valuation of A, B, C. 8 million, 7 million, and 6 million, right? 6 million, they differ by 1 million. So if the first boy proposed 2 million, the second boy to the 1 million, and the other one 0 million. So actually, virtually is a tie situation. Tie situation, what mean tie situation? For the buyer, which is girl, is it worth to spend 8 million, whatever, $2 million on A or $1 million on B? In this case, it's a tie situation because they differ only by $1 million. So that's why you have some kind of connection, more line connection. So this process just continue. You see the connection means that that's your preference. Sometimes you have a tie situation. So for the boys, whenever you have a multiple proposal, so you have a market, so you can increase your demand by increase the demand. For example, every time you increase $1 million. So eventually, you see the boy won since you get the proposed, right? Multiple. By the way, why B cannot really do proposal, although this is one proposal. This is not enough because this is tie situation. But for this one, you can see that X is the sole proposal, right? X only proposed one guy, the only one solution. So X only one proposal. So A can raise its cost to 3. Once it raises cost, then Y, from Y point of view, it's better to marry B or C instead of A. So that link is broken because your asking price is too high. You compare with the valuation. You can see the nice structure, the changes, right? So when this algorithm will stop, it stops when you find the perfect matching. Perfect matching means that you can match A with X, B with Y, or B with Z, C with Y. Right? Initially, there's no perfect matching. Like for the C, there's no perfect matching. So that's the situation. Because for C can only marry Y, but it's competing with B, so there's no perfect matching. So this is actually turned out to be a very interesting algorithm, but again, it's beyond the scope. So if you use money, so it's another market model. So you can take care of the interest of the boys by asking for more money. Right? So you can see that, by the way, the step when this algorithm stops called market clearance price. So that means that's what your price you get for the boys. But you can see the role of algorithm, not only in engineering, but also in economics can play. Right? So I think I cannot spend too much time on this extension, but I would really want you to consider this problem, right? How to do trade so that eventually the girls will get Pareto optimal. assuming that initially they all paired already based on the stable marriage algorithm. But then when you give a preference, not preference, give order powers, how can you increase the happiness of the girls without causing any conflict? Okay, so that's the additional material we discuss. Now let's continue with the chapter. We discussed chapter 2 already. Probably we'll skip that. Maybe we'll discuss chapter 3. By the way, for chapter 2, right, we mainly focus on the complexity. So you should know all the complexity, right? And I give you some sample problem. So basic complexity is that you should know 3 notation. One is O, means at most, right? Then the at least, then equal. Right? So we call this asymptotic order of complexity. Then we look at a couple of sample algorithm, right? How you find the maximum number. It's a pseudocode, so I expect you to write the pseudocode. You don't need to use any specific language. And sometimes pseudocode, you can use some English, right? For example, how you merge 2 sorted subsequence, and you can get a complexity of n, right? That's very simple. And we also look at some kind of closest points in a 2D space. That's the order of complexity of n squared, where n is number of points. Then you want to find in some situation whether there is any 2 subsets that are disjoint. So it's n cubed. The reason is that you have n square pair of sets, right? Then in order to check whether disjoint, you have to check all the elements inside. So that's why it's another loop. So you can see that it's a 3 loop. That's what we discussed. And there are many other problems we discussed, like independent set, and what's the maximum size of independent set, and so on. Okay. Then the last part we discussed is we look at some sample example. Actually, we start with today is an interval schedule problem. Right? It turned out that this problem, you can solve it using greedy algorithm, which is linear. By the way, we're going to spend 2 classes on greedy algorithm, then 2 classes on dynamic programming, and 2 classes on divide and conquer. These are the 3 major basic techniques. Probably you learned already in all the other classes, but we're going to discuss in more details or depths. Then we look at the network flow problem. Then we discuss a problem called NP-complete, which is difficult problem. So far, no one find a polynomial solution. Then we look at some situation, right, approximation algorithm, although we haven't discussed that. So that's the main like overview of this class. Any questions before we move on to the next chapter? Initially, we're doing very fast. The reason I'm assuming that you all know those things, complexity and data structure. So let's overview the data structure. So today, data structure. Again, so I post chapter 3 on the website. Again, assume that you know the data structure. We do very quickly, probably like 10 minutes. The reason we overview only graph. Graph is the most complete in the sense that because all the other data structure can be considered as a special case of graph. So what's a graph? Graph has 2 components. One is the nodes and the other one edge. Right? So nodes usually represent a circle, edge connecting 2 nodes. Although there are many other extensions in some situation called hypergraph, means you can have an edge connect to more than 2 nodes. Right? Just like in a computer, if you use a bus to connect a multiple computers, so it's a bus structure, right? Like network is bus structure. But most of the network they use just regular one, means that each edge connect to 2 nodes. So you have a set like 1, 2, 3, 4, 8. Edge is like 1 connect to 2, 1 connect to 3, and so on. Okay, so that's very easy. But more interesting thing is that why graph is so important. You can represent many things in real life. For example, transportation system, right? For example, in a city, you have lots of highway or street. Then those highway and street consider edge, and street intersection called nodes, right? Or in the communication network, computers are nodes, fiber optic cables, right? Or bus, all this are the edge. And even the World Wide web page nodes, hyperlink connection to the other website, that's the edge. Another popular network is social network. Peoples are nodes, relationship, like a friendship relationship, friends, right? And then many other things, right? And if you look at the electrical circuit, gates are nodes, wire connecting the gates are edges. Let's just look at a couple of simple examples. Suppose this is CNN.com has this web page, main web page. Underneath, they have some kind of hyperlink connect to other, right? Or then each of them may connect to others. So you just follow the web page or website. That's what we call web surfing. I want to go through links. Right? So that's why it's important, because we can represent a www as a graph. And this is another one. This is 911 terrorist network. You can do this counter-terrorism. So actually, this is a hot topic. I just wrote one paper right after this 9/11, where I try to see the structure, social structure of those terrorists. It turned out different person of different color means a different rules. If you recall that there is 4 planes involved, each plane has about 4 members. Right? So this connection really means that each node is a person. The edge means a relationship. Right? So by studying this graph structure, you know how terrorist networks are structured. So one study shows that what's the bottleneck of those terrorist network means that if you take out a couple of nodes, the network gets partitioned, right? And so on. So that's another interesting topic. And this is ecological food web, right? We know the food web network is prey and the predators, right? So one animal eat the other animals, and animal eat insects, and so on. So you can see this is like a food chain. Right? One important thing is how you represent graph. It's very important. The reason is that suppose we represent all this problem in a graph. How you represent a graph. So you can use adjacency matrix. It's very simple. So if you have n nodes, you have an n by n matrix. Then the intersection means suppose you have a link between 2 and 4. In this highlight red, then you put the 1 there. Right? So the number 1 corresponds to a number of links. So you can represent a graph in a sparse graph or dense graph and so on. Okay. So actually, there are lots of theory behind this. Actually, involve matrix series. Actually, all those big data or relationship can represent the matrix. The problem of this one is that a certain matrix are sparse matrix. Like a social network is sometimes not as dense. Why is it not that dense? For example, you have 1 million people, but how about your friends? each person maybe have 100 up to 100. So relatively number of links is relatively sparse. We know that from this matrix, the maximum number of links is about n squared. But in reality, you don't have n square links, right? For the reason that each person has only limited number of friends. Right? So that's why there are lots of series study, like what's the efficient way to represent a sparse matrix, how you do this sparse matrix calculation so that you can compute all this graph very efficiently. Okay, obviously this is beyond the scope of this class. If you're doing computation science, right, or data science, probably they will study this. Just more like a mathematics. And there's another way. If the network is very sparse, why don't we do this one? Is that for each node, just what we mentioned, right? Each person maybe have only 100 friends. Why we just link each person all this 100 friends? Then the average number of data points is number, which is n, like 1 million times 100. See, the size is smaller. But to represent this one, because each person's friendship or the size or friend size differ, so we link all these friends. So we call the linked list. So in this example, for example, we look at number 2. Right? Number 2 has 4 neighbors, 1, 3, 4, 5. So you just put 1, 3, 4, 5 in that order. Right? So why you use the linked list? It's easy because you can easily insert a node. Suppose you have a new friend, you can just insert in the middle. If you a friend leave, you can just delete the link. Right? So this is just one. Or you can use array also. Right? Array means that you don't array of number, but array is kind of fixed, although you have a dynamic array. But that's, I think it's covered already in the data structure class. Right? And there's several other data structure often, but it's just a special case of we call line or linked list. One is a stack. Stack means that it's first in or last in, first out. It means that whenever there's new data, you push the data in front. And we take the data also from the front. So that's a special structure. You can only push data to the front, like pushing. Then we take our data always to the front also. Another one is a queue, means that you open the both ends, front and rear. But that's just some kind of convenient structure for certain application. But all of them just, you can consider as a special type of list or array. And there's probably you heard this called heap, right? Heap is a special tree. Although I haven't talked about a tree, tree is a special type of graph that we discuss next. Right? And we all know this in a graph, you have a path, means probably we don't need to go through this one. You just a sequence of nodes, right? Consecutive sequence of nodes. And a path is simple if all nodes are distinct. For example, if you model this graph as like a city, street, right? And nodes is the intersection of a street. So like when you try to find the one node, shortest path from one node to another node, right? That's one of the typical problem we study. Right? Then we have a concept of cycle, means that it go back. Right? So you see that the previous problem I assigned you, so we're talking about cycle, like from boy to girl, girl to boy, and so on. So that's, and the tree is a special type of graph, but it's kind of unique. There are several ways to represent a tree or property. They are equivalent. Actually, tree is the one that use the minimum number of links and still connected. So if you have n nodes, you only need n minus 1 edges. And a tree is a graph that does not contain any cycle. Okay. So if a graph does not contain any cycle, that's a tree. So all these ones just you can check, right, to prove So by the way, one way to prove for these three are equivalent, you can label this A, B, C. First prove from A, you can derive to B, then B to C, C to A. That's an easy way to prove. Okay, so sometimes the tree, you have a direction, you have a rooted tree, right? Like a parents and children and so on. So I'm not going to go through this. So probably there's a concept of graph traversal. We all know this. Traversal is important that if you want to do search, you want to enumerate all the nodes in the graph. So how you do this one? Sometimes it's a graph can represent like problem space. So you want to look at all problem solution space. You want to see all the possible solution space. You want to enumerate all the possible paths or all the node sequence of nodes. Okay. One typical example is called maze traversal. Actually, it's very useful. So we know the maze, right? Like if you take your friends or go to a park, there is some kind of maze in the park, means that you have one entrance, one exit inside the maze. Now the question is, how can you get around? Eventually you find the exit point. So one way you can do is you have to systematically remember or a strategy to go through all the possible route. Right? So I'm not going to go through all these things. And one of the searching methods called the breadth first search means that you explore all the possible direction, like in a maze, layer by layer. So layer really means start from the beginning, what's the distance? So there's like a 1-hop distance, all the nodes, then you go to the 2-hop distance and 3-hop distance. So you have to systematically enumerate all of them. Right? So this is called the breadth first search. You learn all this in the data structure and program technique. So we're not going to go through that. So there's some property of breadth first search. And compared with breadth first search, you have a depth first search. Right? Probably I get into this. These connect components not really exciting. Okay. And this is a special property of bipartite structure. That's not really interesting. Bipartite graph really means that as a special graph, you can color this graph into 2 colors, blue and red. In this case, like boys and girls, such that the connection among the nodes only from one color to another, either boy connect to girl or girl connect to boy. You never have a situation boy connect to boy. Otherwise, it's not bipartite graph. Okay? So it's very important. And you may think why bipartite graph is still useful. You already saw that in the stable marriage problem. If a graph is not bipartite, you may not find the stable matching. Right? So that's the situation. Sometimes this is more like a scheduling problem. So after the break, we'll talk about this greedy algorithm. Like a machine, your job, how you assign job to different machine, or how you assign the class to different professor so that all classes covered. Right? So all this kind of assignment, stable marriage, so lots of problems bipartite graph. Right? So I'm not going to go through that. There is a standard algorithm, give you a graph, if not, for example, this is a bipartite graph, right? On the left-hand side, just by look, you cannot really tell immediately whether this is a bipartite graph or not bipartite graph. So there's some kind of standard algorithm to detect that. But that's really, I'm not going to go through that. We skip all this. By the way, you don't really need to read all these things, just need to remember. Right? But you need to know that graph, there are 2 types of graph. One is just undirected graph, means there is no direction. But there are some cases that you have a directed graph, right? So there's direction. Okay. For example, web graph, hyperlink, right? Means that a page A point to B. So it's a link from A to B, not B to A. So directed graph has its application. So I'm not going to go through this. Direct graph is basically similar. The only things about the connectivity is a little bit interesting because it's for undirected graph, A can reach B means that B can reach A. But in the direct graph is not, right? A can reach B through a directed path. Doesn't mean that B can reach A. Unless this is so-called strongly connected, means that for every pair of nodes, they are mutually reachable, means from A to B and B to A. Okay, so that's some application. So I'm not going to go through that. The last two concept is a DAG. DAG means a directed acyclic graph. So meaning that there's no cycle, right? But it's not a tree, it's no cycle. So this is called topologic sort order. Really means that it gives you a partial order of all these nodes, like events. So a typical real life example is that every day, like you get up, right? You get up, you have to do a bunch of things. For example, you put on your clothes, put on your pants, and you brush your teeth, eat your breakfast. Right? So there's certain order, but this order not like totally order, means that you don't have to like brush your teeth before you put your pants, or you can sometimes do a reverse. But in some cases, there's order. For example, you need to brush your teeth before you take a breakfast. So that's what we call it's kind of partial order. But it's a DAG, means that there's no cycle. Right? So the order, I mean, directed link really means that particular order you have to respect. Right? Now the question that I give you this DAG, how can you come up this topological sort order, means a linear order. Right? So that's a very basic, right? You learn in discrete math or in the data structure. So I'm not going to go through all these things. And I think with this, we basically review all some of the properties. You don't really need to. Complexity of topological sorting algorithm, we all know that. Okay, so with this, we basically finish. Any questions? We haven't go to the main part. But now let's look at the main part of this class, second class, greedy algorithm. So I think in today's class, we look at the 3 examples. So what's a greedy algorithm? You need to give some kind of formal definition. So imagine that in your real life, right? So your objective is try to maximize overall utility of some process. For example, you want to get rich, you want to have a happy life. Now the question, what's the best way to get rich or get a happy life? In fact, lots of things, future, it's unpredictable. Right? So what you can do is that you do step by step. For example, during your college, you study hard, right? So it's a substage. So what you try to do is do a optimal choice at each substage. Hopefully you'll get a good result or optimal result for the whole process. So that's the idea. So the greedy solution is just say, so solve problem. If you use this greedy structure, you may solve problem optimally, but in many cases not. But in this class, in this chapter, we just gave you many interesting problems that you can solve using the greedy solution. But you remember in your real life, you cannot really do that because many problems looks very simple. If you apply for greedy, you may get the miserable result. Okay. So let's start with the first problem. By the way, this is just quote from a movie, famous movie called Wall Street. Greed is good, greed is right, greed works, greed clarify, and so on. So let's look at the first problem. Right? So the first problem is called interval scheduling. So you know that during the college, just imagine my younger daughter, she just finished college, and during the college lifetime, very, very busy. You have to like taking classes, doing club, right, social, and so on. So the problem is that sometimes you cannot do multitasking. So you assume that each task you can do only one at a time. If there is an overlap, then you cannot accomplish anything. So what you try to do is that give you a bunch of tasks or job, start time or finish time. So this is given, just like a taking class. This class is 5:30 to 8 o'clock. You cannot do any other things. But your objective is that you want to select the maximum number of activity or job a day. So how do you do that? How do you do that? So this will give you example. So job A cross, right, long time. It finish start time 0 and the finish time 6, and the other one is a B and C and D, E. You see there are lots of overlap. And there's quite a few solutions you can select, right? For example, you can select A. Once you select A, then the only choice you can select is G or H. That's it. You only solve two problems, two tasks. But if you select the B, then you can select the E. Once you select E, you can select H. Right? So you have a 3. Now the question is that how you find out the optimal solution? Obviously, you can try all the, silly way is you try all the possible sequence. But any greedy solution means that if you scan the job from left to right, so look at each step locally and make a greedy solution, and hopefully get the optimal result. Right? So this is the solution we're going to talk about. But before we do that, when you see such a problem, you have to analyze this one. So don't jump to the conclusion. Then for each strategy, come up some example to see whether your approach is right. So what's the possible way? You can see that maybe one greedy is that we select the job with a very small duration. So you can maximize your jobs, right? That looks like a reasonable. Another choice is why don't we, since a day start from 0 and at 11 o'clock, so we can start the job with earliest starting time. So we keep me busy. Or another one is that we focus on when the job finish. We focus on what the finishing time. So which is the best one? Before you solve the problem, pay attention. Very important, pay attention. What's the goal? The goal is not to keep you all busy. You want to maximize the number of jobs. Even some job is very long, you just count one. You just count the number of jobs you can do a day. Okay, so this is what we discussed, right? Earliest starting time, earliest finish time, shortest interval. Another one is the fewest conflict. What means fewest conflict? Look at the C. Look at the C. So during the lifetime of C, from 3 to 5, how many tasks it conflict with? A conflict, B conflict, D conflict, E conflict, right? So these are the ones, the C has 4 conflicts. So maybe this number plays some role. So you will think, right? So for each job, count the number of conflicts, schedule in ascending order of conflict, for example. See, any of this work, so what you can do is come up some example, maybe extreme case, but your objective, remember, is to find out optimal result. The first one is the earliest start time. Immediately find a counter example. This cannot get the optimal result. Why? If you look at the one task very, very long, it starts earliest, like in the morning. But this task lasts so long, you can spend the whole day. So you can only do one job. That's not good, right? in reality, you can have accomplished 3 or 4 independent small jobs. So you can see that earliest start time job selection, the greedy, at least for this greedy, doesn't work. What happened to the shortest interval? So look like shortest interval it makes sense, but in the extreme case, it doesn't work either. So suppose you have a 3 job, A, B, C, right? You can see that the darker one is the shortest interval, but it overlaps with the other 2. In reality, you select the other longer one as the optimal result. Right? So this is how you solve the problem, like how you think about this, right? Try different kind of greedy solution or heuristic solution to see anyone works. Although that you try many examples, if you cannot find a counter example, doesn't say that it will works. But if you find a counter example, that means it does not work. So that's the one. Another one, slightly a little bit more complex, means that complex is mean few is the conflict you select. It's not the solution either. For example, like this case, if you look at all the other jobs, other than the dark one, has 3 conflicts, right? Whether the first row or the other row, everyone has a 3 conflict. But the one in the middle has 2 conflicts. But apparently, if you select this one, this is not the best solution, because once you select this middle one, you can only select the one to its left, one to its right. So the total number of jobs you can select is 3. While in reality, the best schedule is select the first row. So with this a quick example, you show that none of these work. Right? So what's the solution? The solution turned out to be simple. Simple means that you look at the finishing time in increasing order. Really means that you start the first job in the beginning of the day. First job, the first finishing time job you select. So that's the one, right? Then you look at the next finishing time one, but as long as compatible with the one you already taken. Right? So in this case, it's a very simple. How you compare with compatible means that as long as it does not overlap. Really, you just need to look at the last one, right? The last one is the one with latest finishing time. So suppose J start is the last one you added. All you need to just look at your candidate one, the starting time and its finishing time of the last one. Are there any overlap? If the start time of the new one you're understudy is before the finishing time of the last one, then it's not compatible. So it's very simple. Right? So let's just look at that example. So in this case, you select what? Not select A, you select B. B is the first one. Is that correct? B is the earliest finish time. Then you look at C. C is not possible. The reason is that C has overlap with B. So that's, then the next earliest one is what? E. Oh, E is okay because the start time is exactly the finish time of B. So you can select E. After that, you can continue with the D. D is not possible because overlap. Then you look at F. Look at this increasing order finishing time. F not possible. G is not possible because overlap with E. The last one is H. So it's a very nice. You just the final result is a B, E, and H. That's what we discussed. Right? See, the nice thing is that it's just a linear scan, although you have to do a little bit of pre-processing. Right, pre-processing. So what's a pre-processing? You need to first sort the finish time in an increasing order, non-decreasing order. So which is n log n. So once you relabel this task, right, from 1 to 3 based on the finishing time, then you just examine this one by one based on the finishing time increasing order. Then it's a linear, it's n. So total complexity is n log n plus n. We focus on asymptotic complexities, n log n. Okay, so that's the complexity. That's why implementation is n log n. Okay. Any question about this? This is quite obvious, right? Then I think we need to take a break. After break, we discuss why this algorithm is optimal. Right? So it's very important. I'll show 3 examples for each heuristic. It's a different way to show optimality. Okay, let's take a break. We'll come back at 7 o'clock. Okay, let's get started. Before I continue, any questions, discussion? It would be good to have some kind of interaction. Anyone want to ask questions? Or any question on the bonus problem? So no one want to say anything? Okay, so if not, let's continue. Let's review what we discussed so far for the greedy algorithm. So if you recall that the problem we discussed is the interval schedule. So give you a set of job with the start time and finish time. And two jobs are compatible if they do not overlap. And your task is to find the maximum subset of mutually compatible jobs. Means that you want to maximize the number of jobs you can complete a day. So for all the algorithms, greedy algorithms, you focus on a greedy approach based on particular parameters, what we call feature. So in this case, it looks like you can define 4 different types of parameters, right? You can look at the start time, finish time, or interval, mean duration, or even more complicated means the number of conflicts. So what we do is that through simple example, we want to eliminate the cases like a start time is not good, right? And we also look at case that the shortest interval in extreme case also not optimal. As long as you find one case, it's not optimal. Assuming that we have a greedy optimal solution, right? But that's a challenge. When I give you a new problem, you don't really know. Greedy solution is optimal. But for this case, I already told you there's a greedy optimal solution. Then it's relatively easy, or you just look at the feature, which feature you use, and all you need to just find one contact example. Right. So it turned out the earliest finish time is the most important. You just sort the jobs based on the increasing order of finish time. Then you examine one by one from left to right. Then whenever you find the compatible one with the latest one, then you just add it. Just run this linear algorithm. It's still the total complexity is n log n because it takes n log n time to sort the task based on the finish time. So why this is optimal? It's very important that in this class you learn how to prove. The bad news is that unfortunately there's no systematic way to prove an algorithm. In worst case, that means for all the algorithms, you have to come up your own solution. But in general, there's several popular methods. One is by contradiction. So in this case, we show the example how to prove by contradiction. So contradiction works this way. We assume that the greedy is not optimal, right? Then we come up with some kind of contradiction and see what happens. So suppose we use I1, I2, Ik is a set of jobs we selected by greedy. Then you have an optimal solution, come up another set of jobs. So we assuming here is like M is larger than K. But we don't really to show this M larger than K. All we need to assume is this one. We assume that I1 equals J1. So the first prefix is exactly the same. Right? So all you need to just find the largest possible value we call R, such that they differ. That's always possible. With extreme case, the first one are not the same, right? So you have a prefix of a sequence or subsequence, they're the same. You see this diagram, the greedy and optimum, you have a longest prefix is the same. And this is the largest possible value. So that means you pick the maximum until they are not the same. Right? Not the same really means that the finish time of the J R plus 1 must be later than finish time of I R plus 1. Why is that? Because in our greedy algorithm, we always select the one with earliest finish time. Right? The early one is the same, but this one must be this one. But then you notice that why not replace this job by the job I select in the greedy one? And solution is still feasible, right? It's still feasible. So that's the contradiction. If it's feasible, then it contradicts to the maximality of R. Because they say R is the maximum value, they are the same. But now, if we replace one, this becomes R plus 1 becomes same. So that's a contradiction. So this is like a more mathematical rigor proof. In fact, you can prove in a very simple way, but it's not really formal, but it's quite intuitive. So basically, if you select initially the first job, right, earliest finish time. So when this job is done, then look at how much time left to select the remaining job. So the time left, right, because you select the earliest finish time, so you have more time than all the other choices, at least the same. Then the remaining, whatever the solution, will not be worse than the other solution. So that's the proof. So the key is that if you select the earliest finish time, so have more time for you to schedule the remaining job, at least at the same as in the rest one. So that means whatever the solution will not be worse than the other situation. So just look at this example. Suppose I selected B, right? That's the earliest finish time. So how much time left? I have from 4 to 11. Suppose your optimal solution is different than me, you select C. Then how much time left? You have from 5 to 11. So I have more time than you. So no matter what's your solution, my solution will be better. Even I copy whatever you have. Right? So that's a simple way to explain. But also it makes sense, right? So because it gives you more option. No less option, more option. Okay, so this is the first problem. Now we're going to, in this class, later we'll look at even more, but in today's class, we look at 2 more and see how you solve it. Then you see all this, you need to practice, and then you get some. But before we do that, for all the problem, we want to look at some extension. So we don't settle for this problem. We want to look at extension. Just like a stable marriage problem, right? I gave you lots of extension. So you have extension with multiple matchings. And today we look at the extension that only care about the interests of girls, how you do this trading. And then we also look at extensions, how to take care of boys by asking more money, something like that. So this one extension is called online. That's actually quite difficult. Really, that means I do not know in advance how many tasks I have. So with no knowledge of future inputs, in general, it's very difficult. If you do not know the future, so how can you know whether this is a good choice, right? Why this is so difficult? Like this one. So the first thing I see it at 0 o'clock, maybe 1.5, I saw the A. Another question, do you take A or you don't take A? You have 2 choices, you take A, then you suddenly see a B, which is a very short, in this case. And so that's why it's very difficult for one. Now, what's the solution? I mean, some kind of compromise is that you can do some kind of batching, means that you can delay the decisions a little bit later to see, for example, I can wait a little bit if this information, more information is coming. For example, initially A comes, maybe after 5 minutes, B and C also come. That tells you about, so this is schedule come up. Then you say, okay, I have this one, then I select B at least. This still may not guarantee it's optimal because you may have another one finish earlier than B, right? So that's why in this case, you don't expect to get the optimal result for the online. Online means that it comes in real time, then it's difficult. A more interesting thing is about weighted interval schedule problem. So what's the mean weighted? Again, for this problem, and use my daughter as an example. So I will tell her that the class is most important. Don't miss classes. Right? So that means each task, each job has its weight. Some is external activity, for example, math club, weight only 1. Some job weight 2, for example, class. Now your objective is not to maximize the number of jobs. You want to maximize the total weight of those jobs. How can you solve that? Again, you think, oh, maybe we can try the one, select the one with the maximum weight, but it's not guaranteed optimal. It turns out this problem can be solved, but you have to use a different strategy. So it will be covered in future class called dynamic programming solutions. So it's more complex, okay? Now let's go to the second problem called interval partition. So now let's again have a fun part. So imagine my daughter graduate and find a job. So went to a data science company. The boss asked her, say that I appoint you as a team leader. So I gave you a set of job to do. You see this set of job, although it says a time, right? You can imagine this like a month, whatever. Like a year, you have that many jobs, this many jobs. Or you can say a time, a day. But your job is to, the question of those jobs, you have to really do something in this particular time interval from 9 o'clock to 10:30. You need one guy to do A. But you cannot do multitasking. You have to hire another one to do C. Right? Now the boss say that how many team members you need to accomplish all this job? I mean, including you. Do you need just 4 team members, or can you reduce it? So the key is this one. You don't want to waste the resource, right? You want to use a minimum number of team members to accomplish all this job. Remember, the key is that each person can only do one job at a time, and there's no overlap. Right? And this can be the same thing as like a classroom, right? So like at Temple University, we are limited by the number of classrooms. So we have so many classes with overlap. So what's the minimum number of classroom to accommodate, for example, 10 lectures? So 4 classrooms is a solution. That's the one solution. It turns out this is not the best solution. The best solution is this one. If you rearrange, you assign person 1 for job A, E, H, person 2, B, G, I, person 3, C, D, F, G, J. It's fine. They save lots of money. You save 25%, right? So boss will be very happy. Say, okay, you're very good scheduler. Now the problem is that how can you come up with this optimal solution? Give you ahead of time number of job and the start time and finish time. You want to use a minimum number of workers to accomplish all this job. Looks very similar to the previous problem, but it's different, right? Although each job of finish time, start time is the same, but objective is different. You want to minimize the number of workers in the team to accomplish this job. So what's the solution? So this one, you have to observe some, before we come a solution, you need to observe some kind of property. So there's one property, key observation is called the depth. Depth. What do you mean depth? Depth means that you do a vertical cut along the line, time. You see at the 9:30, you look at this 9:30, right? You see that at the 9:30, there are 3 jobs. So this gives you a low bound. Really mean the number of people in the team must be at least 3 people. Maybe 4, maybe 5, but minimum is a 3. Okay. So that's you get some idea, right? So that means a low bound. And this lower bound can help you if your algorithm turn out that they will generate a number or team member, which is equivalent to the low bound, then you don't even need to prove that because no other solution can beat a lower bound. Okay. So that's one. Now the question, does there always exist a schedule equal to the depth of interval? Right. So that's the thing. So if you even look at this one, and you can find out that that's not very good. If you do a cut. You anytime do a cut, how many jobs you cut through? 3. So that means 4 is not necessarily the best one. Although, right? So that's the one. Okay, so let's look at this one. It turned out the greedy solution is you examine a job at a time. Start from the starting time, increasing order of a starting time. So which makes sense. Imagine that you're the boss, right? The team leader. So my daughter is a team leader. So whenever a job comes, so I just do a schedule because when your start time comes, you have to do the job. You allocate one of the team members. Right? The question, how you allocate? Right? So the allocation is the follow. But here is use a classroom. It's the same thing, a classroom and the team member. So you start with a number. You also sort the job, but not sort based on the finish time, now sort based on the start time. So it takes n log n, right? Then you do a linear scan from 1 to n. So you see that the start time 1 to n. This is allocated classroom. Initially, you don't allocate. It means that you don't hire anyone. The reason is that you may not have any job there, you don't hire. Right? So it's kind of dynamic. Then you from the task 1 to n, you have n job. Your lecture 1 means the first job is compatible with some classroom. What mean compatible with some classroom? So it means that you already have, suppose you have a K classroom, right? Classroom with K. Compatible means that there's one team member is not doing anything. It's free. Obviously, you are assigned to this team member, right? So in this case, you schedule a lecture to that classroom. So whenever someone is free, classroom is free, you just assign. What happened that currently you have an allocated K classroom, no classroom are free. Really means all are busy, or means all team members are busy. What does it tell? Busy means that their depths, right, already K. Now you have a new one come, so the depths become K plus 1. So you keep in mind this concept called the depths, right? Because when the task arrive, if all the team members so far are all busy, means the depth is K. And you have a new job coming, the depth become K plus 1. Okay, then you allocate a new classroom. You see, you allocate a new classroom. Means you hire a new team member, so which is initially D and D plus 1. Right? D plus 1. Actually, D is the number of classroom. So if no classroom available, then you have to use another classroom, or you have another team member. Right? So this just process continue. This turned out to be the optimal. Why this is optimal? So the key things just I mentioned that for all the classroom, you allocate, right? Currently, suppose it's a D. Then the new job comes, if all the classrooms are busy, that means the depth is already D. Then you add the one more, it becomes D plus 1. Okay. So that means the classroom are allocated match to the depths of the problem. That's why it's optimal, right? So you probably don't need to go through all these details. Okay, so basically the same idea. Means that if you allocate only when there is no classroom available, when no classroom available means the depths are already the current numbers, you add one, right? So the depths of the lectures is more than the current one. So the all classroom schedule is optimal because your allocation strategy match the low bound. Okay. But again, this is kind of lucky because for this particular problem, you can find a solution that match the low bound. But in reality, life is not that simple. First of all, for many problems, you don't even know the low bound. Right? For this one, is you know low bound. Sometimes even a problem you can find low bound, but there's no solution that can match the low bound. Okay. So there are lots of gap. So right now, all the problem I gave you is like sounds very rosy, means that life is good, right? For all the problem I can solve. But unfortunately, I cannot lie to you. These are the easiest problem. That's why I have a textbook, give you all the easy problems. The real life is much harder. But it's still interesting enough. It's like a quite practical, right? Any question? If no question, then let's continue with the last problem. Called schedule to minimize the lateness, okay? So just imagine, go back to my daughter's problem. So she works there for 2 months or 3 months, the COVID hit. Then the boss said, the company run out of money. We cannot really afford to hire lots of workers to solve the problem, right? But I changed the problem, the requirement a little bit. Little bit really means that you can do your work at any time. There's no like a time slot. I just gave you a bunch of work to do. And I know that since you only do one person, you cannot really finish the job. But the difference is that in this case, each job has some kind of deadline. For the job one, say finish 2 days from now. The other job, maybe 3 days from now. So each job has a deadline. So your job is to schedule them based on whatever the criteria, duration or based on deadline, such that I know that you cannot finish everything before the deadline. But at least I want you to minimize the lateness. What means lateness? For example, a job deadline is 3 o'clock. You finish at 5 o'clock. Lateness is 2. The other job deadline is 6 o'clock. You finish at 9 o'clock. The lateness is 3. So I don't really care accumulative lateness. I just care about the maximum lateness. So one, you late by 2 hours, and by 3 hours, I only punish you for the maximum lateness. So what you try to do is minimize this maximum value, okay? So that it's a slightly different problem. So you understand that? So you see this problem or complexity of problem, not just based on the problem, right? Based on your objective. So that's why I emphasize many, many times is that when you see the algorithm problem and later you go back to real life, work, pay attention to the goal. What's the objective? It should be very, very clear, right? So it's a single source resource process, one job at a time. So that means only one person do the job. So my daughter doing all this job. Unfortunately, each job is some duration. The boss assigned say that you can do any time. It's up to you. But each job has some deadline. So this table really means job 1 takes 3 hours, but deadline by 6 o'clock. And this job 2 hours, the deadline by 8, right? So you see, you have all this. Can you imagine this is just like a real life situation. Every day we have so many things to do. Unfortunately, something is more urgent, it's like a deadline. What you try to do is just to do all the work. Obviously, you miss some deadline, but you want to minimize the maximum lateness. Okay. So that's the thing. So if a job start at time xj, then finish time must be sj plus tj. T means the duration, right? So you have a start time and finish time. It's a very simple math. Lateness is defined as either zero. Zero means that if you finish before deadline, no lateness. But if you finish after deadline, then it's a time to finish time minus your deadline. That's the lateness, as I say. If a job deadline is 6 o'clock, you finish at 9 o'clock, the lateness is 3. But I don't punish you accumulative lateness. I punish you the maximum lateness. That's very important. If I punish you on the maximum accumulative lateness, it should be sigma, but now it's a maximum. Now try to schedule all the job to minimize the maximum lateness. Right? So this is one. So let's just look at a real scenario. Then before we come up with a solution, again, try it like a first problem, right? What's the parameter you want to use for greedy? So suppose you start with 0 o'clock, you start with 3, right? D3. So which is deadline 9. And then the duration is 1, so you finish 1 slot, right? Then you start 2, job 2 ended. Here, there's a lateness. There's no lateness, right? Because you finish 3 before deadline. See, all this is easy until you start here, right? Then the job 1, when you finish at 8 o'clock, unfortunately for task 1, the deadline is 6. Okay, I already missed 2 hours. Right? So this lateness is 2. Then for job 5, duration 3, it can be a little bit more deadline, 14 hours. It turned out this is fine because I finished at 11 o'clock. I'm fine. So no lateness. Then number 4, durations of 4. Wait. Is this 4? Yeah, 4. Yes, 4. Duration is 4. Deadline is 9. Deadline 9. But unfortunately, you finish at 15. So that means the lateness is 6. See, for each job, you calculate the lateness. Right? Then you find the maximum. You want to minimize the maximum. So what's the optimal solution? So again, we look at this based on choices. Maybe we can do the shortest processing time first. Right? Obviously, you will see that that's not right. The reason is that if you don't look at the deadline, right? So it's impossible. Right? But we can look at some example. So one is just to start with the shortest time first to do first, right? And another one is the earliest deadline first. So you do the thing that has the earliest deadline. Another one is the smallest slack. What means the smallest slack? Means that we need to see the TJ. TJ is a duration, right? So it means that your deadline versus your duration. So deadline minus duration is called slack. So basically, the slack means that the latest starting time without missing the deadline. That's the slack, right? That's a deadline minus duration. So means that it's the time, latest time you schedule this job without causing lateness. So the smaller one, probably it's more urgent. You should do. It makes sense, but it turns out this is still not optimal. Okay, let's look at, again, what you do is just do counterexample. Suppose you say that shortest processing time first. If you without looking at deadlines, obviously it doesn't work. The reason is that you look at this one, job 1. Execution time only 1, right? Is that execution time only 1? So the other job is 2, execution time is 2 or 10. So it looks like a shortest job is better. You do early, then, but what's the problem? The problem, if you do 1, then you do 2, then 2 will miss the deadline by 1 unit. Because it turned out it's a very bad situation, means that execution time deadline is the same, right? So, but the deadline for 1, or it's a short job, the deadline is very long, which is 100. So that's why in this case, it's better to do 2 before 1. Counterexample. How about the smallest slack? Remember, smallest slack means that deadline versus duration. So it looks like this problem is the same like the previous one. The only difference is deadline is different. So if we look at the smallest slack is for the second job is 0, means that you cannot really afford delay, because otherwise it will cause a delay, right? Cause a delay, lateness. If you schedule 1, then the 2 are missed by 1, so the lateness is 1. But in this case, the difference is the deadline for 2 or first job is 2. So it's very early. If you do job 2 first, so after 10, then you do 1, then it's 11 o'clock. So 11 o'clock versus 2 o'clock, so you miss by 9. So the maximum lateness become 9, right? So in this case, ascending order of a slack time doesn't work. Counterexample. Now, what's the best solution? The best solution is the earliest deadline first. Right? It's kind of intuitive. Earliest deadline first. So the previous example, you just look at the deadline. In some sense, it's very easy. You first sort the job based on the deadline. See that? Or the deadline. So you just, the job 1, the deadline, this one was 6, then 8, 9, 9, 14, 15. So it's ascending order, right? Then you just do all this one. And in this case, the maximum lateness is 1. Only 1 missed the deadline, is for this 9. All the other one do not, because their deadline is later, right? Deadline 14, they finish at 13, 15 is perfect. So lateness is 1. So that's kind of fascinating, right? The problem we looks like a similar, and all of them have a optimal greedy solution. But the question is which parameter you use for the greedy solution. So you have earliest finishing time, and you have another one is the earliest start time schedule, and this one is earliest deadline first. Okay. Then it's simple. All you need to just allocate. Whenever you allocate a job, you add its duration with the interval. So you set the time to a new one, right? You start a new start time and finish time, just add the duration. Then you update your time again, then you schedule to the next one. Okay. Now the proof a little bit involved. Means that how can you prove this is optimal? There's no other solution can beat this one. Although intuitively it's very simple, but how you prove mathematically very rigorous. Okay, so this is sometimes you need, before you prove, you need some kind of observation to make some kind of basic assumption of observation. So in this case, you will see that this is one obvious observation. For any optimal solution, you don't want idle time, right? Idle time is just to waste the time and increase the lateness. So this is a very important observation, means that you don't want to waste any time. Whenever you finish, you schedule next one. Obviously, our solution does not waste any time. So that's obvious. Right? So then you assume that all the solution, there's no idle time. It's just the order, which order you want to do. Then the second observation is very important. It's called the schedule inversion. So inversion really means that suppose the job you already allocate sequence in terms of deadline first, increasing order. So you see this one, D1, D2, Dn means a deadline. So the later one has a longer deadline, right? So suppose you have two adjacent adjacent one. Adjacent one means scheduled adjacent. So such that the label I is before J. This really means that J's deadline is after I's deadline. So listen carefully. It means that I's deadline is before J's deadline. Okay. So immediately you can think about this inversion will increase the lateness, at least the same as if you swap it, right? Because I's deadline is late, at least no earlier than J. But you schedule this one after J, it will increase its lateness. So this, in this way, then easy observation means that our greedy one has no such inversion, right? No inversion. Our schedule is because we always schedule based on deadline first, no inversion. Then the remaining thing is that for any schedule, right? Remember we labeled this task from 1, 2, 3 to this one is based on the finishing time increasing. So whenever you see a number swapping, we call this inversion. So how many different schedule? Our schedule is 1, 2, 3, 4, 5, 6 to n. Any other schedule is a sequence of inversions, right? For example, if you have a 3 tasks, our schedule is 1, 2, 3. Some other schedule is 2, 1, 3. Some schedule is 3, 2, 1. The other schedule is 3, 1, 2. So all kind of other sequence is just a bunch of inversions. So I think you learned this probably in the algebra, right? So there's some, I forgot which proof. It's proved by inversion. So you just consecutively keep on invert, eventually, and you get a sequence with no inversion. So that's the basic proof, okay? So the main idea is any schedule can be converted to, so that means we are better than all the other one with the inversion, okay? So that's the basic proof. I don't think we need those details, right? So the key is that you just do a bunch of adjacent inversion. You can invert it to 1, 2, 3. Unfortunately, I don't have, I think if I can write this one, I show you how to do an inversion. Yeah, maybe I do here. See if I can do, yeah, I think I can do here. Just copy one, have one blank page. Oh, maybe I don't even need to. So optimal one is 1, 2, 3, right? So suppose you have a 2, 1, 3. So what you can do is just you keep on invert. Invert means that 2, 1, 3, 1, 3 invert. Then after this inversion is 1, 2, 3. You see that? So that means each time inversion, the situation is not getting worse. So that's all you need to prove. So then you can prove any kind of sequence. Suppose the 3, 2, 1. So you can do 3, 1, 2, 1, 2 invert. Then 3, 1, 3 invert, right? Then you invert 2 and 3, 1, 2, 3. But remember each adjacent inversion to next one, so the performance will not get worse. Or in other words, we find a general proof that any kind of schedule, after I do this kind of inversion, the solution we're not getting worse. And I mean, our is the best one. 1 to 3 is the best one. Okay, so that's pretty obvious. So I think with this, I don't want to overwhelm you. I want to give you a summary, but later I will give you some general one. The summary I give you is this. It's an early page, but that's kind of important. So greedy algorithm just show that after each step of greedy algorithm, its solution is at least as good as any other algorithm. So that's why it's like my proof, right? My proof means after you start with a finish time first. So that may give you more option, more time to schedule. So it will be at least as good as all the other one. I mean, interval schedule, right? For the maximum number of tasks. And sometimes the structure is very important. Interval partition. Remember this, like you have a bunch of jobs, you want to hire minimum number of team members to finish job or a classroom schedule. So this is a little bit more involved. It's called discover a simple structure bound, in this case, the depth, asserting that every possible solution must have a certain value, in this case, the depth. Then show that your algorithm always achieve this bound. So if you achieve this low bound, no one can beat you. So that's the solution. And the other solution is that you exchange argument. In this case, like swapping, right? So inversion. So gradually transform any solution to the one founded by the greedy solution without hurting its quality. Right? So that's what the inversion can do. And there are many other algorithms I'm not going to discuss. Probably you learn this in the data structure or program technique. One is like Cusco prims, that means find a minimum spanning tree, right? Or minimum, spanning tree. Dijkstra algorithm is the shortest path algorithm. That's probably one of the most beautiful algorithms in the world, right? How you find the shortest path, giving you a network. And Hoffman code really means that for an event, multiple event, right? And with different frequencies. And then for each, then you want to find the coding scheme so that on the average, you're detecting the code, the time you spend detecting the code is minimized. So why this detecting code is important? I mean, suppose I assign an event with a code. If you have a long code, for example, 6 digit, it takes 6 units of time to decode, assume. So your idea is that you want to assign the frequent event with a shorter code, like one bit, and less frequent event with a longer code, right? So this is like a coding theory, so that on the average, you want to minimize the time. So it's a very classic solution. It turns out there's a greedy solution. Give you events with a probability distribution, so you can find the best code. It's the variable length code. Remember, code has a different kind of code. In the computer, usually learns a fixed length code. Really mean like if you have a 16 instruction, so you just need a four bits, right? 4 bits to represent 16. So each has 4 bits. But Hoffman code says that no, we can use a variable length. For frequent one, we only give 2 bits. Less frequent, maybe you can use 6 bits. See, the overall time you spend on decoding is the number of bits you use times the probability. Right? So this is the one interesting observation. But because of time constraint, we're not going to discuss that. See, the good news is that you see we give a problem that you find all this greedy solution. The key is how you find the parameter, right? And we come up with different kind of proving method. But bad news, I already told you that there's no universal solution. Unfortunate is that look at the problem, you cannot even tell, even probably the smartest guy in the world. You ask, this problem, you can find a greedy solution or not? No one knows. unless this problem is already studied or very close to the problem you know. Right? So don't be fooled by the simplicity or complexity of the problem. Like, oh, looks like the problem is difficult, or looks like easy. Some look simulate two problems very similar. One has a very good solution, simple solution, other one, they don't. Right? Just the example I mentioned about interval schedule, very simple, linear, or if you consider sorting, n log n. But if I put a weight, then it's much more complex. You have to use dynamic programming. Okay. So since we have about 10 minutes, I want to discuss 15 minutes. So we want to give you some more, a little bit more advanced material. It's outside the textbook, but it's kind of interesting. I gave a problem, this problem to my students when I accept the PhD students. I give them those tests. So all this we already discussed, right? So it's very clear. Now let's look at extension. So each problem has some extension. And one extension looks like it's okay. I remember going back to the lateness. Suppose this boss to my daughter say that I change the problem a little bit. For each task, I have so-called concept called release time. Release time really means that the earliest time you can do the job. It's not like in the previous they say that you can do the job anytime, right? Start from 0. But for certain job, I have this release time, means that you cannot do this job before 7 o'clock, for example. But you have to, the deadline is 11 o'clock. So give you a range. It turns out this problem is very, very hard. No one can find the optimal solution, I mean, efficient solution. So interval partition with a different release time is turned to be very difficult. Okay. In general, there are many so-called scheduling, task scheduling. Like the problem I just mentioned is all related to so-called task schedule, right? So you have a job, and then you have a worker, means like a computer. So let me just give you a classification so you know that there's hundreds or thousands of jobs, different type of model. So if you want to know a little bit more detail, I have a textbook on this called Distributed System Design, in which I dedicate 2 chapters on the schedule. So the schedule has, one is a task model, means a job model. So far, all the job we assume independent, is that correct? Means I give you 10 jobs, they're independent, although they have some kind of release time or finish time. And there's many other things, it's more complicated. For example, jobs are related. For example, you have some job, you have to do it in a particular order, like a topologic sort. For example, you get up in the morning, you first need to brush your teeth before you take a breakfast. So that means you have to do job, brush teeth first. After, then you can do breakfast. Right? And there are some job is more complicated. Means that there's some job you need lots of communication, especially nowadays, right? You learn this neural network, machine learning, divided into different blocks, but there are some kind of communication. Even sometimes they have a just precedence order, means that you first do this stage, then the next stage, right? Once this stage complete, do the other stage. So that means precedent. But sometimes you have communication, means that there's feedback loop. Okay, so that makes things more complicated. And another important thing is that there's one popular model called pipeline model. So what I mean pipeline model? Mean that you have a bunch of jobs like in a batch. Just imagine pipelines like assembly line in a factory, for example, in a car manufacturer, right? So if you assemble a car, you have to do certain sequence, step by steps. So that's called like a flow shop, job shop, or open shop. Right? Means that you have a job, you have to follow certain steps. But each step you have a different machine, means independent. So how can you schedule this job in the pipeline fashion? and you achieve some kind of optimization. Right? So famous example, manufacture assembly lines. Right? And even in the machine learning, this is what we do recently. Like offloading. Offloading really means that if you're running a machine learning, the neural networks, and in your local cellular phone, right? The good thing, the cellular phone is very convenient. You get data, you do processing, but the processing power is limited. What you can do is offload your computation to a remote cloud or edge. Right? So there's a trade-off. The trade-off is that if your data you have to upload, it takes some time. What you gain is a computation, but you waste time in the communication. So it's very interesting. It's like some kind of pipeline schedule. What's the optimal schedule? Where you offload some of the code from local side to remote side. Right? And this is used actually a lot in the autonomous vehicle. Right? Autonomous vehicle means that now each car is like a big computer. So you have all kinds of sensors, then doing all kinds of sensing, and then you need to make a decision. Like autonomous car, you want to avoid collisions and all that, right? Now, if the problem is that if you have a limited in terms of computation, can you offload some of the computation through internet, right? Wireless internet through roadside. And another challenge is like you download some information from the satellite, for example, map. One of the challenges is how you download when the car reach a particular location, you need to get accurate, high resolution map. That's very important. But the download the map takes some time. So you see, oh, this is like a pipeline and scheduling problem. So this is very exciting field, although this is beyond the scope of this class. Just tell you that on the scheduling, there are so many different scheduling. Now let's talk about some interesting solution. This will start today and we'll continue next class. General problem solution. Unfortunately, we don't have that. Actually, you learn a lot in high school, especially if you are very good at math, you're involved in a math competition. And we already learned that the proof by contradiction, right? Proof by contradiction, we already showed. Proof by induction, you prove this in high school or even college, right? Induction. For example, how you show that the particular equation is correct, combinatorial equation. So you can prove by induction n is 1 is correct. You assume k is correct, then you prove that k plus 1 is also correct. Right? But I want to show you two examples I give. One is sometimes when you see it looks like a very difficult problem, but you can convert this problem to another problem. Then it becomes very simple. That's obviously you have to use the imagination. Another way is so-called the proof by accounting method. Remember we talk about like a stable marriage, we introduce money, right? So it's some kind of like accounting method. But if you think carefully, this is very exciting. Actually, money doesn't play too much role. Imagine a guy married a girl, right? So you want the guy want to get the maximum amount of money from the girl or wife, future wife. What happens if they married? Once they married, they become one family. So the money becomes, the girl's money is still your money and money still belongs to the girls. So it's kind of interesting accounting method. So let's start one. If I can finish one, that would be good. If I can finish two, then. So the first problem is this one. That's called the M problem, lifetime, and it's ACM. You know, ACM is the largest computer society, very prestigious. So every two months, they give us like 3 questions. So first question is easy, second one is harder, third one is no one solve it. So this is one of the questions they give. They just say that on the chopstick, there is 25 ends, 25 ends. These ends initially placed in any kind of location. You don't really know location. You can't anywhere. Could be all clustered in the left end or right end, doesn't matter. But they always move. They move at 1 centimeter per second. You keep on moving. But the problem is that look at these two middle ends, when they hit each other, they will change the direction, go the opposite direction. But when they go to the opposite direction, right, like this one go to the opposite direction. No. If this one goes up two direction, this one will go this one. We hit this end, right? Then this end both will change the direction. You see the middle ends will keep on changing the direction whenever they got hit. But the rightmost and leftmost ends, when it get hit, it go all the way to the right, it falls and die. The left one also get hit by this one and go back and die, right? So you know the speed of each end. The only thing you don't know the distribution. And makes things more difficult is that initially you have 25 ends, you don't know the distribution, and you don't even know what's the orientation of the ends. They just keep on walking. When they hit, go to the opposite direction and walk. Suppose the chopstick is 1 meter long. Now the question I ask, how long does it take? How long does it take before all these ends fall and die? What's the time? How long? So how can you estimate that? Right? So this turned out to be, looks like a very difficult problem, because initially I gave this problem to my PhD students. Most of them come up with very complex mathematical equation. Why is that? You introduce one variable for each end, and then the distribution you don't know, that's very complicated. You have to give assumption like a location, then they calculate, right? Whenever they calculate how many minutes before seconds they hit, and then reverse. So eventually it come up something, but no beautiful result. It turned out there is a very nice solution. You don't even need any mathematics and to find out. What's the solution? You change the problem. So how you change the problem? Just imagine that each end wear a hat, different color. When two ends meet, they change direction. They also exchange a hat. So the key thing is when they reverse direction, they exchange hat. Very important. Now you pay attention, not the movement of end, you pay attention to the movement of hat. Now the hat is always moving from left to right or right to left. It will never change the direction. And hat always move at a constant speed of 1 centimeter per second. So then you know that the maximum lifetime is what? Right? So you already know. So it's just goes through from left end to the right end. And the beautiful thing is that you don't even need to know the distribution of the ends. You can find out the average life of those ends. The reason is that just look at any location of an end, there is a 50% of chance going to the left, 50% of chance going to the right. So it doesn't matter where's the location of the end. So the average lifetime is half of the length of the chopstick. Right? So in this way, you can solve this problem very easily. You see that these two ends meet, they exchange hat. Then you focus on the lifetime of a hat. So why this is correct? Because you can establish one-to-one onto mapping between hat and end. So when a hat falls, it means that one end falls. Right? So that's why, so you can establish this kind of mapping, then the problem is solved. Okay, so solution is just introduce a new variable called hat on the end. Then you solve this problem. Okay, I think with this, we finish this. Again, this is like a very special problem, means that how you solve to give a solution and how you prove and how you do some mathematical calculations. So next, I will tell you another problem. Maybe I can give you now, but you can think about, you see, this key is that you establish a lifetime of a hat is one-to-one bijection between hat and end. Then it's, so this one you don't really need to, you can think about this. So now you just read the first line, then we can talk about, oh, there's a typo there, but I will correct. So imagine there is a group of students, in this case, like 13 students in my class. And for example, I have a 13 student, research student. I partition into K group. For example, 3 group. So we have a group study. Right? So last year, and then the repartition this 13 students into K+1 group, like a 4 group this year. I assume that each group has at least 1 student. And prove that there exists at least 2 students, so that their group size getting smaller in the new year. The group size means that initially I'm in a group with 5 students, but this year my group become 4 students or 3 students. How you prove that, right? So think about this, then we can discuss next time. Okay, let's stop right now. Again, there's a typo should be changed to. I think I changed the problem, but I forgot to change the solution. So I should change it. So 2020 to 2021, right? Not the 2018 and 2019. Okay, let's stop for today. And then I need to stop the recording. Okay, so I'll see you next week. And I will post this one maybe later this week.